Okay, so this function models how much bacteria is in a certain place. We're supposed to find the rate of change in the number of bacteria, so we need the derivative. So I'm going to distribute the 2,000 before I start taking the derivative, just so I have nice, distinct, separate terms. So 2,000 times 1 is 2,000. 2,000 times this stuff, it's 8,000 t over t squared plus 100. Now when I take a derivative, because I have two separate terms, it makes taking the derivative easier because you can take a derivative of each individual term. The derivative of 2,000 is just 0. It's a constant, so we can forget about it. Derivative of this, though, is probably best done using the quotient rule. We could call this f of x, and this is g of x. And if you remember, the quotient rule says that if you're taking a derivative of two functions that are being divided from one another, then it's f prime g minus f g prime all over g squared. You could write those off to the side if you want. The derivative of f is 8,000. The derivative of g is 2t, because the derivative of t squared, the 2 comes down, multiplies, gets reduced by 1. Derivative of 100 is 0. So if you plug all those in, we got 8,000 in for the derivative of f, and times g of x. That's sorry, I said g of x. It's t, right? It should be t there, but most of the time when we're given the quotient rule, it's in terms of x. But okay, so that's derivative of f times g minus the f function times the derivative of g. So we got 8,000 t times 2t. And that's all being divided by g squared. So this is g, and if we're squaring g, it looks like this. There's g, there it is squared. So that is our derivative. It's just kind of ugly, hard to type in. So let's expand the top. Maybe we can combine some like terms. We got 8,000 t squared plus 8,000 times 100. Add an extra 0. 8,000. 1, 2, 3, 4. No, that looks right. And then, so I just distribute the 8,000, just doing algebra here. And then over here, this is 8,000 times 2, so that's 8,000 t times 2, so that's 16,000 t squared. And that's all over, we'll keep this factored for now, t squared plus 100 squared. So we can combine these like terms, subtract those, that makes negative 8,000 t squared plus 800,000. That's all over t squared plus, that's all over t squared plus 100. And then we can factor out an 8,000 from the top. Getting closer. I think there's going to be something that cancels out. So I'm going to factor out a negative 8,000 just so my leading term is positive. Negative 8,000, we've got t squared, and then if you divide 800,000 by negative 8,000, and that's negative, so it's negative 100. So it's minus 100. And that's t squared plus 100 squared. There's a little bit extra we can do, believe it or not. This is still the same derivative. This is the same thing as this down here. We would just keep rewriting it with algebra. But this can be factored. This is t minus 10 and t plus 10. So we got negative 8,000, and then it's t minus 10, t plus 10. That's not going to help us though. Okay. I think we'll just leave it there. That's as close as, that's as small as we can get it. Okay, so that's the derivative that we got. And these are just asking you to plug in certain values in for t and then to simplify. So the first one is just plugging in 0 and then carefully simplifying. I don't know if they want it as a fraction or not. I guess if they don't say a decimal, then we got to put it as a fraction. So let me do 30 just to see if there's any like calculator problems that might come up. mouse to work. Okay, so we got negative 8,000. And then we're plugging in 30 squared minus 1,000. Sorry, 100 over 30 squared plus 100 squared. Okay, so I'll do the numerator and denominator separately when I do these. Got 30 times 30 minus 100 times negative 8,000, negative 6,400,000 in the numerator. Okay, I'll try not, I guess I won't type it. Negative 6 million. Then 400,000. The mouse just isn't cooperating today. Okay, and then in the denominator, I'm going to do 30 squared plus 100, and then I'm going to square that result with my calculator. Get rid of that. 30 squared plus 100, and then square that. So that's a million in the denominator. So I've got negative 6,400,000 divided by a million, so you can just cancel out some zeros. Cross simplify, so that's negative 6.4, or as a fraction, I guess I'm not sure which one they want. It's negative 64 over 10, which is negative 32 over 5. So I'm not sure if they want a decimal or not, but I would write negative 32 over 5 for an answer there. Just because they didn't say to the nearest 10th place or something like that. I just checked. They put in negative 6.4, which is the equivalent. Okay, so I guess decimals are okay for those ones. So I leave the other ones for students to do. That's just plugging in numbers into the derivative. Oh, shoot. It says interpret the results from part B. Okay. I got it. So I do have to. Okay, I'll pause. I'll plug in 0, 10, 20, and get those numbers. Okay, so there's my answers for part B. They want us to interpret the results. So at t equals 0, when we plug in 0 in for the derivative, we get a positive number. So the population is increasing. At t equals 10, we got a slope of 0. So the population is staying the same. I'm not sure what the drop down is, but it's neither increasing nor decreasing. And at time t equals 20, we got negative for a slope. So that means the population is decreasing. And at time t equals 30, we still have a negative, so it's decreasing, just at a slower rate. For part D, they want us to evaluate at the second derivative. So we don't have that yet. We have just the first derivative. So for the second derivative here, I'm going to rewrite just a little bit. I'm going to distribute that negative 8,000. Because when we take a derivative, it's nice to have separate terms. That way we can use the power rule. And then this right here, that's t squared plus 100 in parentheses times t squared plus 100 in parentheses. So if you do that out to the side, that should be t to the fourth plus 100t plus 100t. So that makes 200t. 200t squared. 100t squared plus 100t squared, yeah, and then plus 100 times 100. So 10,000. Okay, I just rewrote the derivative in a way that makes it easy to find the derivative of the top and the bottom, because if I want to find n prime with two derivatives, if I want to find acceleration, then I need to use the quotient rule. Derivative of the first function with the second kept the same, plus the derivative of the second function with the first function kept the same, just like we did up above. Okay, so this is our f. This is so we need to know what f prime is for our formula. So that's not too bad. The 2 comes down and multiplies. Negative 16,000 t Still a t in there. And then this is the derivative of constants. That's nothing. We're done with the derivative of f. And the derivative of g, the 4 comes down and multiplies. The 2 comes down and multiplies. And then the derivative of constant's nothing. So that's the derivative of g. So if we plug everything in where it's supposed to go, the derivative of f, do I have that right? It's a negative 16. I think I have an extra 0 here. Yeah, the 2 comes down, multiplies, that's negative 16,000, not negative 160,000. Okay, there's the derivative of f with g kept the same. I'll use this for my g, the factored form. It's the same thing as what we wrote over here, okay? But that's a little neater to write. And I'll show you how we can use a calculator for the next part. And then it's supposed to be f kept the same. So this is our f. Is it really that many zeros? 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah, 1, 2, 3, 4, 5. There's our f times g. That's all over g squared. So I'll use this as my g. If you square something that's being squared, then the powers on top of powers multiply. So that's t squared plus 100 to the 4th power. Okay, so that monstrosity is the second derivative. And we might be able to distribute, cancel some terms, but man, if all we need to do is plug in these values for part D, then let's just go ahead and use some technology, okay? Because that's a lot of algebra. It's easy to miss something when you're copying stuff down. Hopefully I haven't missed anything yet, or else I'm going to have to redo this whole thing. So what I've done is I've gone to the website desmos.com/scientific, and I'm going to plug this in. I'm going to write this all out. I'll start with a fraction. Type 1 divide 2 to get my fraction going. At the top, I got negative 16,000 t times t squared plus 100 squared plus negative 8,000 t squared plus 8,000,000, 4t to the third plus 400t. That's all over t squared plus 100 to the 4th. Okay, and the way this is going to help us is that if you want to figure out for like it's the first derivative here, I'm trying to move the screen. First derivative at t equals 0, then all you have to do is go over to the desmos.com/scientific in your formula. Just watch out, that t is multiplying, so I'm going to replace that t with times 0 here. And this t is also going to be 0. And this t, I got to remember to put times, or else it'll think you're just trying to add a 0 onto negative 8,000. And then same thing here, I got to put a times symbol. I'm replacing every t with 0, and then the computer will do all the calculations for us. So now the times 0, and so that's 0 squared. And it's 0. The whole thing implies to be 0 when you plug in 0. And then you can do the same thing for n prime prime of 10. So the second derivative at 10, you can plug in 10 for 0. Replace all those zeros with 10. And we get negative 4. So we can keep going in that fashion. I'm going to check though, because I'm going to have to remake this whole video. Yeah, it's working out. Oh, I need the other answers. So the other ones, if I was to plug in 0.256, 0.288. Okay, I think we're ready for the final part here. Interpret the answers. At t equals 0, the rate at which the bacteria population changing is constant. It's 0, right? We got a slope of 0. That means it's neither the slopes are neither decreasing nor increasing. At t equals 10, the rate of the population is changing is, we're going down. We're decreasing. Let me just see what these drop downs are, though. Staying constant. So decreasing, like we said for this one. If it's negative, it's decreasing. And if it's positive, like these two, it is increasing.